All right, in this section, we're going to take a look at nonlinear models. Although this course focuses primarily on linear models, it's good to see these to compare and contrast some of the similarities and the differences between these two types of models. Okay? So let's taking a look at nonlinear models in a single section is like taking a look at algebra in a single 1-hour lesson. It's just not going to happen. So instead of looking at every possible or even several possible linear models, or rather nonlinear models, I'm going to go ahead and pick on one and have that serve as an introduction to this much bigger field. Okay? So let's make an assumption. All right? Let's say you have a population size. A population size, we're going to go ahead and call it P of t. And let's say that that population is a function of time. We're going to assume that there's no other variables other than time. If you wait long enough and know how much time has passed, you can figure out what your population is. Okay? So assume P of t denotes population size at time t. Our population can be a population of people, of rabbits, or whatever you like. Here we're just going to say a population. Okay? Now, if you make the assumption that the population size changes directly related to the size of the population, if we assume that the rate of change of our population over time is equal to the population size times some constant, where k is constant, this can then, so this is a differential equation, obviously here. Derivative is equal to some constant times the original function. But this is one that we've already seen. And you say, yeah, that's a linear model. Well, not just any linear model, it's the exponential model. It's the same, it will yield the result of the exponential equation, the kind that you learned back in algebra. Okay? So here, if we assume that the derivative, the change in population, is equal to some constant times the current population size, where again k is some constant, then this yields the exponential model. This solves as the exponential model. You say, well, aren't you going to show that? Well, we could, but again, that's linear. But here we want to show something a little different. You say, well, what do you mean different? It's a population. Populations grow exponentially. We see that all the time. Well, actually, that's not quite true. Population does not grow exponentially. That's only half the story. Here, let's go ahead and make a different assumption. If instead we make a much more realistic assumption, if instead we assume population changes dependent on P, or rather on a function of P, sorry I said that wrong. If instead we assume population changes dependent on a non-constant function of P, which we will call f of P, then we get what's called the density dependent hypothesis, which will look similar to this. We get that the rate of change of our population, instead of being equal to our current population size times some constant, rather it's our current population size times some non-constant function. This gives you a much more realistic model, because now we're saying that there are external forces besides just time and your current population. There might be things like diseases. There might be things like resources, a limitation on resources, a limitation on space, things like that. And so this function gives you a much more flexible and a much more real kind of conditions. Okay, but what is this f of p? Can we even possibly know what it is? Well, let's, again, continuing with new assumptions, our previous, I should probably label this. This is what we call the density dependent hypothesis. So over here we had a constant k. Here we have some non-constant function. But what is that non-constant function? Well, we can experiment with different possibilities. The simplest one, however, is to say, well, this might, maybe it's a hyperbolic inverse function. Yeah, maybe it is, but why would we jump to that directly? Why wouldn't we just say, well, this is really pretty simple and doesn't give us the complete picture? So let's just take this to be the next simplest function. If this one's too simple, why do we jump to the most complicated thing we can think of? Why not jump to something that's just slightly more complicated than a constant? And that would be a linear function. So we begin by assuming that our f of p is linear. Okay, so then that means that our f of p is going to look something like this. It's going to be some constant, I'll call it C1, times our population plus C2. Again, linear. Constant plus first power, that's a linear function. Okay, well, we need some information to figure out what these constants are. Right? This p is the variable of our function, but C1 and C2 are just some constants. They're some numbers. Where are those going to come from? Well, we have some conditions on our population, which we should probably denote here. So we begin by assuming f of p is linear, which again gives us this, with a maximum population at some time which we'll call k, at time t equals to k. So this is going to be a big difference between our current assumption and our previous assumptions, where population just grows unimpeded. Whenever you see population growth in algebra classes, they always look like this. They're exponential, and they keep growing, which of course we know that's not really realistic. There's got to be some limiting factor. Again, I mentioned diseases, lack of space, lack of resources, and things like that. So here we're going to assume that whatever environment we're in, and again, now we're making a more realistic choice here, rather than just some unimpeded growth, there's going to be some limiting factor, whatever it might be. Okay, so we're going to assume that at a certain time, that's it. You've reached it. You've gotten to the maximum population size that this environment can contain. Well, if you're at that time, your derivative of growth, the change in your population is 0. Okay, since dp dt is equal to 0 when t is equal to k, right? Your population growth isn't growing anymore. You've reached the maximum. It's not going to get any higher. And we know that, let's see, p is a constant. Again, when you've reached your maximum population, your population won't change anymore, so that's a constant. Since this is equal to 0 when t is equal to k, and p is constant when t is equal to k, then, okay, well, this is a constant. Oh, sorry, this is 0, and this is a constant, so this must be 0. So that means f at that time k, when you've reached your maximum population size, is going to equal to 0 as well. You have some constant times something is equal to 0. Well, then this function must be equal to 0. So f at k is 0. We also have to have some initial condition, which we always can measure at the very beginning of our experiment. We have at time 0, or rather at population 0, we have some initial condition, which we'll call r. We'll say this is our initial population size or something like that. Consider an initial condition where f at 0, again, our initial conditions at time 0 here, or rather at population 0, at 0, we have some initial condition of r. Okay, so we have two values that we know the results for f at. F at k is equal to 0, and f at 0 is equal to r. Okay, so now we can use those to create a small system of equations for this function here. Thus, let's see. If I plug in, let's see, p is equal to k here. So I get C1 times wait, what did I just do here? Oh, sorry. Yeah, that's right. So here I'm going to go ahead and use this one. So if I go ahead and plug in p is equal to k, then my result's going to be 0. So I get c1 times k plus c2 equals 0. For my initial condition, I get that if p is equal to 0, then my result is r from this function. So if I plug in 0 here, I get c1 times 0 plus c2 equals r. And so, well, right here, this just goes away, and c2 equals to r. Here, if you plug in c2 equals r, you get c1k plus r equals 0. You can subtract the r, divide by k, and you get c1 is equal to minus r over k, just like that. And so plugging those back in gives us a way of finding our f of p, our coefficient function here. F of p is going to equal to c1, which is negative r over k times p. Negative r over k times p. Oh, I shouldn't write it with parentheses. That makes it look like that's an argument of a function. I should just write times p, like that. And then plus my c2, which is just r. Which, as I look at this looks a little weird because the minus is in front. So I'm going to make just a aesthetics choice here and flip it around. So my constant will be first. And I get r minus r over k times p. Okay. So going back to my density-dependent hypothesis, I now have a reasonable candidate for the function f of p. Now, if I made other assumptions, this, for example, saying, oh, I don't want this to be linear, I want it to be quadratic or cubic or sinusoidal, I would get something else. But again, we're starting from a constant for the exponential model, and we're saying, okay, let's not go wild. Let's just have the next simplest function, something that's just one step more complicated than a constant, and that's a linear. And if that's the choice we're going to make, then this is a reasonable choice for that function. So our hypothesis, our density dependent hypothesis, that's going to become, let's see, dp dt is equal to my f of p, that is r minus r over k times p, like this. Not the whole thing, just like that. And then that f of p is being multiplied times p, which I'll write in the front. Again, just an aesthetic choice. So I've got dp dt is equal to f of p times p. Okay. In many books, you will note that, in many application books, you will note that r and r over k are often replaced with just more simplified constants. Yes, r does come from an initial condition, and yes, r over k does come from a condition based off the initial size and the maximum population size, but oftentimes we just care about the fact that they're constants. So note, most of the time these will be replaced by simply a and b. And r over k is replaced by b. Okay. Which leads us to the way you'll find this equation in most in most textbooks and application, and that is dp dt is equal to p times a minus b times p. This is what's called the logistics equation. Logistic equation. And it is another, and I would argue more realistic version of population growth. Now notice this model is not telling us what p is equal to, right? We don't have an equation for population. Rather, we have a differential equation that involves population. But we can solve this. And in fact, this is the reason I've chosen this particular problem as the one that I'm going to focus on in this section. Nonlinear models can be very, very extensive, can be difficult, and can require many more techniques than we do not have in this course. However, this one, in spite of the fact that it is a nonlinear model, does yield to some of the techniques that we've already seen. All right, so let's go ahead and solve this logistic equation to create the solution to population and what we often call the logistic function. All right, so here we go. What I'm going to do is I'm going to take this equation and I'm simply going to separate variables. Thankfully, it does yield to one of our more basic techniques. Here, we're going to go ahead and write this as, okay, I'm going to take 1 over, now this is a function of p, so I'm going to bring that over this way, 1 over p times a minus bp dp is equal to, and since I brought everything over here, all that's left is 1, right? It's like I'm saying I divided all this away, so all that's left is 1 dt. Okay, now here I can go ahead and break this apart using partial fractions. Notice that these are two distinct linear factors in my denominator here, so I can always separate those. And I'm going to end up with something over the first factor plus something over the second factor. And then, of course, that something, we can go ahead and use a nice shortcut because these are distinct and linear. If they weren't distinct or not linear, then we'd have to go through the whole process of not separation of variables, of partial fraction decomposition. But because they are distinct and linear, we get to use a nice little shortcut here. We get to say, okay, because of p, I would not be allowed to plug in the number 0 for p, right? I can't plug in 0 here because 0 times anything is 0. And dividing by zeros is undefined. Oh, okay, so our little shortcut for this specific situation of partial fractions is, okay, I can't plug in 0 because of that. Okay, cover that up and now plug in 0. Oh, I get 1 over a minus 0, which is 1 over a. And that's my numerator here. You might remember that little trick from pre-cal. Likewise, over here, because of this factor, I'm not allowed to plug in a over b. Because if I plugged in a over b, the b's would cancel, and I would get a minus a is 0, and dividing by 0 again is undefined. So because of this factor, I'm not allowed to plug in a over b. Okay, so cover it up and now plug in a over b. Oh, I get 1 over a over b. Oh, 1 over a fraction, that's the reciprocal of that fraction. So I get b over a. Neat little shortcut that you may remember from pre-cal. For a partial fraction decomposition. Over here on this side, I'm just going to go and leave this as it is for now. But now I can integrate each of these. That's a logarithm, that's a logarithm. Remember, a and b are constants. So we can go ahead and integrate here on both sides, giving me 1 over a times the natural log of the absolute value of p, a minus, and then I've got, let's see. Oh, I've got an extra equal sign here for some reason. Not worry about that one. So here we've got b over a times the natural log of the absolute value of a minus bp. Oh, but then here we would have to then divide by, so that should be a plus. But then here we'd have to divide by negative b, because that would be the derivative of our denominator. And so here the plus and the minus gives you a minus, and the b's cancel out. And then over here, the integral of 1 with respect to t is just 1t. Now, of course, all these have constants of integration, and I could put a plus c1 and plus c2 and plus c3. But since they're all constants, I'm just going to go ahead and merge them all together and just say this is plus c over here on this side. All the constants will come together. So here I've got 1 over a, natural log absolute value p, plus a negative is minus, and then my b's cancel out there. So I get 1 over a natural log a minus bp equals t plus c. There's a nice property of logarithms that says whenever you subtract two logarithms, you can divide their arguments. So this becomes 1 over a natural log of the absolute value, p over a minus bp. Hooray for the algebra of logarithms here. And on this side, I've got, still nothing's happened, so just t plus c. I'm trying to solve for p. Remember, that is ultimately our goal. We're trying to find an equation that solves our differential model here. We're trying to solve for p. So here, we're trying to isolate p now. I can go ahead and multiply the a to the other side. So that's going to be natural log absolute value p over a minus bp equals, let's see, a times t plus a times c. Now remember, a is a constant and c is a constant. So when you multiply a constant times a constant, you just get another constant, right? So here I'm going to write AC for now, but of course, in the next step here, I'm just going to go ahead and merge those together because that is just another constant. Okay, now let's see here. What have I got? Okay, so now I need to get rid of the logarithm. So I get P over A minus BP equals E to the AT plus AC, like this. Now, right here, this is equal to this part right here. Let's see, that's going to be e to the AT plus, again, multiplying two constants just gives you another constant, so I'll call that C2. But now, whenever you have a sum in the powers here, really you're just multiplying. Right? This is the same as e to the AT times e to the C2. But since that's a constant, we can call this C3. However, as you've already seen in the previous sections, the custom is when you're adding or subtracting a constant, you call it plus C. But when you multiply by a constant, you call it times M, which gives us a very strange coincidence here. Since M is our coefficient, and we typically write coefficients in front, we end up with meat, which is kind of ironic for a equation that governs the population size of different populations, since in most biology and ecology books, this would be used to model the population size of, say, for example, rabbits, some kind of prey animal, which is kind of an ironic result here, meat. ME to the AT, of course. So here we've got P over A minus BP is equal to ME to the AT. And of course, we don't say meat, it is actually ME to the AT. So now here, let's see, I'm going to go ahead and multiply this to the other side. So I get P is equal to, let's see, just going to be A times ME to the AT minus BP ME to the AT. And since that has a P as part of its factors, I can go ahead and subtract and factor it out. So here I get P times 1. This was already a minus, so I'll move it over as a plus. So I get 1 plus BME to the AT, like this. And then over here I'm left with AME to the AT. And now we're just about done, because here we can now divide to the other side and we get a result. P, which I haven't been writing it, but remember P is a function of time, as was defined at the very beginning. It's a population in terms of time. P of T is equal to, and of course here you do see your variable T, is equal to A ME to the AT over 1 plus B ME to the AT. Now, while this is the result, oftentimes, again, in application books, you'll see, I'm actually not quite sure why they do this, but this is a very common thing. They will write it a way that looks a little different from this, and the way you get the common rewriting of this is you simply multiply on top and bottom by e to the minus AT. I have no idea why they do that, and maybe it's just to get rid of the fact that this is meat. I don't know, but this is often written as P of T equals AM over, here these two divide out, these two cancel out, so you end up with BM plus e to the minus AT. This is the most common way of writing this, which is the solution to the logistics equation. We've just solved this differential equation here, and the solution to the differential equation, the solution to the logistics equation, is often called the logistic function. Logistic function. We can take this and with one additional step, make it a little more directly usable. Let's say, for example, our population had an initial population size, which we'll call P0. If the initial population was p sub 0, whatever size that might be. And what we mean by that, again, is if you plug in time 0 into p, you're going to get p0. Okay? Then p0 is going to equal to, we can come over here and plug in 0 for our t. So here we end up with am over bm plus e to the 0, which that's e to the 0 is just 1. So here we end up with am over bm plus 1, like this. And that's going to be our p sub 0. Okay. But that means that we can solve for m in terms of p0. So here we can go ahead and write this as am is equal to, I'm going to go ahead and multiply this to the other side. So I get p0bm plus 1 times p0 is just p0. I'm trying to isolate m here, so I'm going to subtract this to the other side. I get am minus p0bm equals p0. Here, m is a common factor, which I can factor out, leaving me m times a minus p0b is equal to p0. And finally, I can divide this to the other side to isolate my m, and I end up with m equals p0 over a minus p0 times b. Because that m is the m in the numerator and denominator of the logistics equation, although this is the way you'll find it in many books, in application, it's often easier to work in terms of the initial population size. So you will often see it in application written this way. Thus, our p of t, which again can be written as am over bm plus e to the minus at. We can plug this in here and simplify. Because you have a fraction within a fraction, you have a fraction up here, you have a fraction down here. What you'll do is you'll just find the common denominator and simplify out. You'll simplify the complex fraction. So in the end, what you get is a times p0 over b times p0 plus a minus b times p0 times e to the minus at. And this is an alternate version of the logistic equation, the logistic function, but this one is in terms of the initial population, which is a little bit more useful in application because you can just plug in initial values directly here. This is just an alternate form of, again, what we call the logistic function. This logistic function has some properties, in fact, very nice geometric properties. Or I guess geometric's not quite the right word. It has some nice analytical properties that show up on a graph, let's say it that way. Okay. The first one is probably the simplest one. If you take the limit as t approaches infinity of p of t, okay, well, let's see. If t approaches infinity, okay, well, that doesn't have a t, neither does that. Neither does this. Only this has a t. And as t approaches infinity, e to the minus at goes to 0. Right? Remember what the graph of e to the minus at looks like. Since it's an exponential, it'll have exponential growth. Oh, no, it's got a minus here. Oh, so it's got exponential decay. It's going down this way. So as t approaches infinity, your exponential is going to 0. So here, this part's dropping off, and all you're left with is a p0 over b p0 plus a minus b p0 times 0. All right, as t approaches infinity, this approaches 0. But anything times 0 is 0, so this part is 0. And now here, p0 divides p0, and all you're left with is a over b. So in the end, those values that show up here in your equation, regardless of which form you're using, a over b is what happens to your population size eventually. It is your end result as t approaches infinity. The next one is just about as simple, even if it takes an extra moment to think about it. And that's what happens if you take the limit as t approaches infinity, negative infinity of p of t. Well, again, these don't have t's. Only this does. And as t approaches negative infinity, our exponential function will grow forever. Oh, but then you have a constant over something that's growing to infinity. Oh, we had a theorem for that all the way back in Cal 1. If you have a constant over anything that grows to infinity, that whole thing will go to 0. As t approaches infinity, this part is going to, as t approaches negative infinity, the exponential is going to infinity, and so any constant over something going to infinity times some other constants, whatever, we don't worry about those, this whole thing will go to 0. Now, our third property is going to take a little bit more effort, but is a nice result. Let's consider the second derivative. Remember, the first derivative of p with respect to t is how all of this got started. It was what we called our density-dependent hypothesis. So we know the first derivative. Right? The first derivative is dp dt is equal to this stuff, which, again, we replace the r and the k with a and b. So really, we should be using this one. dp dt is equal to this. So the second derivative is just the derivative of this stuff, isn't it? Yeah, that's right. But we get a nice result when we do that. So here, the second derivative is just the derivative of the first derivative. And the first derivative is, again, our logistic equation. So really, it's asking what's the derivative of the logistic equation. So here, let's see, that's going to be p times a minus bp. Keeping in mind that even though t doesn't appear here, it's implied. P is a function of t. So it's not all constants. We're not going to get just 0. Okay. All right, so we're taking the derivative, and this is a product. Oh, okay, so let's use the product rule. Nice, simple Cal 1 technique. Take the derivative of the first one, which I'll just call dp dt for now, times the second, which I'll just leave that alone, a minus bp, plus, now I want to leave the first one alone, just call that p, times the derivative with respect to t of this second part here, which I guess I can just actually take the derivative. I don't have to write it as d anything. So the derivative here of the second part, a is a constant. Derivative of a constant is 0, so don't worry about that. And the derivative of negative bp, well, negative b is a constant, so I'm just going to leave that alone, negative b. And then the derivative of p is dp dt. So I've gone ahead and used the product rule. Derivative of the first one, derivative of p is just dp dt, times the second, plus, now leave the first one alone, and then derivative of the second, right here, derivative of the second. Derivative of a is 0, since it's a constant. The derivative of negative bp, the negative b stays the way it is, since it's a coefficient, constant coefficient, and p, well, the derivative of p is dp dt, just like it was earlier. But now you notice dp dt is a common factor. I can factor that out. So I get dp dt times, oh, let's see, I've got a minus bp plus minus bp. Now these are gone right here. So this is just minus bp and then another minus bp. That'll be minus 2bp. Like that. Notice right here that dp dt is known. Right? We even before we solved any of this stuff, dp dt was known. It was our initial logistic equation, even before we had the logistic function. So dp dt can be replaced by p times a minus bp. All right, so right here, that's going to be p times a minus bp times a minus 2bp, like this. Okay, so that's going to be my second derivative. So you say, okay, well, we found our second derivative, so what? Notice that because this is a nice set of linear factors, they all have zeros. I can find the zeros of this. You say, okay, so, well, if you remember from Cal 1, wherever you have zeros of the second derivative, those are potential inflection points. We can consider what it's going to look like on a graph. Finding the zeros of this here, I guess I don't have to do that here. Thus, d squared p dt squared, the second derivative, has zeros at, okay, well, if p is equal to 0, then that's it, p equals 0. Then we've got if a minus bp equals 0, then you would end up with p is equal to b over a. oh wait, no, other way around, A over B. And if this one's equal to 0, you get the same thing, except now there's a 2 on the B. So you'd end up with P is equal to A over 2B. Like this. Now, one thing you might notice from these two numbers is that they're the results from our previous properties. You never reach 0. You only approach it asymptotically. Likewise, you never reach A over B. Right? You never get there because you would have to reach infinity to get to A over B. You're never going to quite reach these. So you would have inflection points here if you ever got to them. But from the previous two properties, we know we never get to those, property 1 and property 2. So property 3 tells us there's 3 possible inflection points. But properties 1 and 2 tell us, well, 2 of them you're never going to reach. So this is the only one you're ever going to reach. Okay? Since P approaches since P of t approaches 0 and A over B asymptotically, then of course they're never achieved. Those are never reached. You never get there. So that means that our only inflection point is going to be at A over B. A over 2B. Thus, our only inflection point is at P equals A over 2B. So putting this all together, we get an accurate, or perhaps maybe not accurate, we get a more accurate representation of population growth than we had before. When you consider population growth to be exponential, you're missing half the picture, literally. Here, we know that our graph will approach 0 as you go to the left, asymptotically. You're never going to quite reach it. Okay, so there's an asymptote right here, population 0, whenever you go to the left. When you go to the right, you're going to have a upper bound of A over B. Right? You're never going to reach it. It's just going to get closer and closer to that. Okay, so you're going to have an upper asymptote of population equals A over B. Okay, well, A over 2B is just half of this. Okay, so halfway between 0 and A over B is A over 2B. That's your halfway point between here and here. So I've got P equals A over 2B. So now our graph will approach this line to the left asymptotically. At time 0, this is our initial population. This is P0 right here. All right, so now you look at that and you go, well, my graph grows exponentially. Of course it does. That's what I've been taught about population growth since probably high school. I'm old. I don't remember when we first learned this, but I feel like I learned it maybe even in middle school. And talking about, I remember that there was the example of the foxes and the rabbits, and that's done in biology. And we talk about exponential growth. But that's only half the story, literally. Eventually, you reach some middle point. And now the forces of growth are going to be counterbalanced by some other external forces, diseases, limitations in food resources, limitation in space. You can't overpack things, otherwise they can't flourish. Anyone who's ever had a garden, you got to occasionally trim some plants back, otherwise the rest of them don't have enough nutrients. So after a certain point, which is going to be our inflection point, our population will still continue to grow, but it'll bend the other way. It'll be almost logarithmic in nature here. It's going to bend this way, and it's going to follow the upper bound. Notice again, you never quite reach that. Our upper bound is asymptotic, just like our lower one was. You reach it as you approach infinity. So your population will slowly taper off. This is what is called the logistics curve, and it is a much more accurate representation of population growth. If you're looking at it from an exponential point, you're only looking at half the story. It is exponential, approximately, up to a certain point. And then external forces take over, and clearly it's not. So this is what's called the logistics curve. Sorry, I keep saying logistics. There's no S. It's just logistic. This is the logistic curve. And it's nothing more than the graph of our logistic function. And that logistic function is nothing more than the solution to our logistic equation, a nonlinear model. And with that, we conclude this section. Again, this is by no means a especially important nonlinear model. It's not an especially important result. I mean, of course, it is useful and it is important in some fields. But here I've chosen this not so much because it is of particular importance to our course, but rather because it was accessible. Note that we did solve this using separation of variables, which is something that is completely accessible to us, right? Separation of variables. Linear modeling is our main focus in this course. Nonlinear modeling is something that you will see in later courses, both in math and in application, and you'll dive much deeper into those as well. But until then, hope you all found the comparison to linear models useful here, and if you have any questions, please let me know. And I hope you all have a nice day.